Well, hello again, ladies and gentlemen. It's Mr. G here today to talk to you about Lesson 4 in our continuing unit on permutations and combinations. And today we are going to talk about now combinations. Now you may, for those of you that have watched the last couple of lessons, we've been dealing with the idea of permutations, which look an awful lot like combinations, but the big difference there was that the order mattered in which you picked. Today we're going to mix things up a bit. We're going to say, well, what if order isn't as important as you might think? Again, this lesson is dealt with as an investigate for the first portion, so I would challenge you to pause the video and go through it yourself for the first little bit to really try and get an understanding of what exactly we mean by order versus no order and things like that. For those of you that are a little more worried about it, just follow along, because here we go. The first question asks, if 5 sprinters compete in a race, how many different ways can the medals for first, second, and third place be awarded? Well, this is just like the questions we've dealt with in the last couple of lessons, and that's the idea that for first place, we have 5 different ways that we can distribute them. After that, there's only 4 people that can get second place, and after that, there's only 3 people that can get third place. All that together means that there are 60 possible ways of awarding first, second, and third. Now, this may remind you of the fundamental counting principle because that's what it is. If you upgrade to the last couple of lessons, we've been dealing with this idea of permutation notation, which says we have 5 objects, and if we need to permute them in 3 ways, well, that's just equal to 5 factorial over 5 minus 3 factorial, which is just equal to 5 factorial over 2 factorial, which is equal to 60 ways again. So, counting principle was the first way we learned. Permutation notation was the second way we learned. Either way you go, it doesn't matter. We end up with the same answer. Now, does the order of finish for the fastest 3 matter here? Well, if you watch the Olympics or have done track or anything of that nature, you know of course it matters. The first person across the line gets first place, and the second person across the line gets second place. So the answer is absolutely yes, it does. And this is an example again of a permutation when we have 5 objects taken 3 at a time. Okay, now let's mix this up a bit here. Let's say, okay, instead of first, second, and third, if 5 sprinters compete in a race and the fastest 3 qualify for the relay team, how many different relay teams can be formed? So now we're just saying the fastest 3 are going to get on the relay team. It doesn't necessarily matter what order they finish in, those top 3 are going to get in there. So say we're looking down on the track here and we have these 5 lanes, and we'll call this particular runner A, B, C, D, E. Remember from previous lessons, it's an awfully nice way of dealing with things if you put it in letters, because then you're dealing with strings of letters instead of some sort of abstract picture. In this case, if we take a look here, here is what we're saying the results are, that the first 3 are in the relay team and the last 2 are not. So if we have A, B, and C that make the relay team and D and E that don't, there's something really important that happens here. If we take a look, A, B, and C have made the team. But in the same way, they could have crossed with BAC, they could have crossed with CAB, they could have crossed with ACB, and I think you're starting to see a pattern here, BCA or CBA. Any way that they crossed the finish line in this manner meant that they all still made the team, but they didn't necessarily finish first, second, and third. This is the idea here of order doesn't matter. Does not matter for us. Any way that they came in, they were going to get in. The same holds true for D and E there. They could have crossed as D and E, but they also could have crossed as E and D. Either way, you know, they're not making team, right? So it's just not going to happen for them. But again, order didn't matter there. Well, this looks awfully similar to the idea of when we were arranging identical objects and we had to eliminate the different permutations that were involved with those particular combinations so that we only got a true count of how many times that particular combination happened. And if you remember, what we did is we ended up with 5 factorial, because 5 is the number of objects, and we had to divide out the number of possibilities for the identical set of 3 and the identical set of 2, and we ended up with 3 factorial, 2 factorial, and that was just equal to 10. And much like we did at the end of lesson 3, where we used this in an extension type question, it's the same idea here. All we're trying to do by using this math here is we're saying, you know what? All of these different combinations count, but we don't really need to worry about those because all of them are equal to this ABC, and we don't need to worry about that one because D and E is just fine. So does order of finish for the fastest 3 matter here? Absolutely not. In this case, top 3 make it, end of story. So in this case, we're talking about this idea of a combination now of 5 objects taken 3 at a time. And that leads us to the big definition, and this is where we're going to start to get, or see some confusion rather, between permutations and combinations, but there's a really simple way of remembering this, and that's the idea that a combination is an unordered arrangement of distinct objects, okay? So permutations, the order mattered, first, second, third. Combinations, it really doesn't matter what order we come in, so long as the top 3 or top 4 or top however many are counted. We have an equation for this, and much like with our permutation notation, we have this idea of n cap CR, which is equal to n factorial over r factorial and n minus r factorial, where r in this case is just how many of a particular set are we trying to take. Some people call this the choose function. You may read about that online. But either way, r in this case has to be a value between 0 and n. You can't have more than the whole set, and you certainly can't have less than 0. And there you go. So in this case, we'll just draw a nice little arrow around here. All we're doing is we're taking n factorial, which is just the number of possible arrangements of a given set, and we're dividing out the number of repeats. So the denominator in this case divides out the number of ways the items are ordered. And like I said before, this is similar to the idea of having permutations where we were taking out the repeat occurrences. Okay, so let's use this beautiful equation in an example. So let's roll down here to the examples. I'll say again, I'll just keep rolling along, but it is a great idea that you pause at some points and you start trying to work on these yourself. But without saying anything else, I'll just keep rolling through. So as I said in the previous lessons, language matters here. And I'm going to give you a little hint box here on the side to deal with. And there's some language, there's some particular words that you can key on to tell the difference between a combination question and a permutations question. So I'll give you the quick little note over here. And it's the idea that if you see the word select, that probably means you're doing some sort of combination type question. And if you see the word arrange, that usually means a permutation. Taking a look at question 1. In ABCD, how many ways can you select 3 letters? Well, our box works out beautifully here. And the idea is we are using combinations. In which case, let's just use our newfound notation. If we have a set of 4 and we're choosing 3, using the equation we're given, that's 4 factorial over 3 factorial, 1 factorial. And that's just equal to, well, that's just 4. So again, you know that the button in your calculator is math probability number 4, which is the exclamation point. If you don't know, come see me, come ask your friends, do whatever you got to do. But at the end of the day, you should end up with 4. Sweet. What about number 2 then? How many different committees of people can be formed from 7 people? So again, none of our keywords are here, but we just need 3 people out of a set of 7. It doesn't say anything about, one has to be the president, one has to be vice president. Just 3 people. That's another combination type question. So in this case, we again we have 7. And we're going to choose 3 of them. And that's just equal to 7 factorial over 3 factorial, 4 factorial. Again, I'm just using the equation from the previous page. And that's equal to 35. Nice. Okay, what about B then? How many different committees of 3 people can be formed from 7 people if the first person selected serves as the chairperson, the second person, So now we're starting to see here that we actually have a particular order that we have to deal with. Look, we need a chairperson, then we need a treasurer, then we need a secretary. Which type of combining or arranging are we dealing with here? I hope you said, it looks like permutations, because that's exactly what it is today, my friends. We're using permutations in this case because the order is going to matter. So that's 7 factorial over 4 factorial, and we end up with 210. If this equation looks funny to you, I say go back to lesson 3 and take a look. Hopefully you've done the homework and you've already covered these a whole bunch of times. Looking at question C, we're asking if the group of 7 people consists of 3 males and 4 females, how many different committees of 3 people can be formed with 1 male and 2 females? So this question is a little different now because we actually have to break it up into 2 separate parts and then use the counting principle at the end. So let's start off with the easiest one, not that any of them are overly difficult, and let's take a look at males. What it's said here is that we have 3 of them and we would like to select 1 of them. So 3 choose 1 would give us the answer to that. And with females, we have 4 females, and out of that we're going to select 2 of them. So either of these would give us the number of combinations to select males and females. However, we want both of them, so in this case, counting principle says let's multiply them together. So we're going to have 3 choose 1 times 4 choose 2, and we're going to end up with a beautiful number, 18. I'm not going to go through the formal equation like I did previously. I'm hoping by now that is redundant. So either way, you should end up with a number of 18. Okay? Which leads us to the last and trickiest one of this particular section. If the group of 7 people consists of 3 males and 4 females, how many different committees of 3 people can be formed with at least 1 male on the committee? So, again, you break this up into different sections, but now we're talking about different cases. So let's talk about this in terms of cases. And the first case is that we have 1 male. And if we have 1 male, well, we've already dealt with that. We have 3 males and we're selecting 1, which means we'd have 4 females and we're selecting 2, and we end up with 18. But what then happens if there's 2 males? Well, if there's 2 males, we took 3 of them, of the originals, and selected 2, which means out of the females, we started with 4, but you only select 1, and there's only 12 different ways of dealing with that. So you see how we needed 2 in the first idea and 1 female in the second idea. So in the third case, where you need 3 males, we're going to select 3 males out of the total group of 3, and out of the 4 females then, we're not going to take any of them because they're all going to be males. And if that's the case, we have 3, we're selecting 3, there's only one way of doing so, given that ABC is the same as BCA, etc., which gives us a answer of 1. So the total number of ways that we can create the committee of 3 people with at least 1 male is equal to 18 plus 12 plus 1, which is just equal to 31. So again, when it asks for questions saying at least or at most, that means you have to count every type of situation along the way. In our cases, it was the number of males from 1 to 2 to 3, giving us our total of 31. So never be afraid to break down questions. Remember, the fundamental counting principle is on your side. So that's pretty much the standard types of questions that way. Let's take a look at a more numerical based type question. We look at a question like this: evaluate the following, and I'll scroll up for you. We have 100 factorial divided by 3 factorial times 97 factorial. If you do this in a calculator, you're going to get a big whoa overflow, and it's not going to do it for you because 100 factorial is a ridiculously huge number. So what do? Well, we've dealt with a question similar to this before, and that's the idea of, think of 100 factorial as 100 times 99 times 98 times 97 factorial, and that's all divided by 3 factorial 97 factorial. Well, 100 factorial will blow your calculator up, 97 factorial will blow your calculator up, but look what happens when we rewrite it like this. 97 factorial goes away, and look what we end up with. We end up with 100 times 99 times 98, the rest is gone, divided by 3 factorial, which is just 6. Well, this number now is easily done in your calculator, and you should end up with an answer of 161,700. So understanding what factorial means and how to separate it is going to be crucial to being able to do questions like that. Let's take a look at something a little different. Let's say we have question B here, which is solve n choose 2 is equal to 21. Well, shoot, we don't know what n is. We need to solve for it, which means we need to know something about the actual equation we're using. And the actual equation we're using says, again, n factorial over r factorial, but r in this case is 2 factorial, times n minus 2 factorial, and that has to equal 21. Well, that doesn't really help us too much. We have a whole bunch of n's, but remember, we can take n factorial and rewrite it as n times n minus 1 times n minus 2 factorial, and all that is divided by 2 factorial is just 2 times n minus 2 factorial. Well, that's all equal to 21. Well, that helps us out a lot because now n factorials will cancel out, and we'll end up with this easier expression, and I've seemed to run out of space, so we're going to go like this, and I'm going to write it right below. We are just left with now n times n minus 1 is equal to, this 2 will just multiply up here, is equal to 42. Well, you're looking for a number times the next number below it is equal to 42. Well, we should know that 7 times 6 equals 42. So when we're looking for n is just equal to 7. And it's just that simple. You don't need to use quadratics. You don't need to FOIL this out and then deal with it that way. Flat out, if you know that a number times the number directly to the left of it multiplied together equals 42, knowing your multiplication tables, you should be able to come up with that quite easily. We've dealt with counting different ways of combining people. We've dealt with how to actually use factorial notation and all that sort of jazz. Now it's time to use the typical type of combination sort of situation, and that's the idea of playing cards. So for those of you that may not know all of the statistics about playing cards, let's just remind you of this. You need to know about all these suits, you need to know about what the cards count up to, etc., etc. So there are 4 suits, right? Spades are black, clubs are black, diamonds are red, and hearts are red. Okay? Now, within each suit, we have 13 cards. Of these 13 cards, there are 3 face cards. And those cards are jacks, queens, and kings. So, knowing what the colors are, knowing what the face cards are, and knowing that there's a total of 13 cards, That's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So 13 total cards. You need to just fundamentally know these sort of things if you're ever going to have a chance at solving any of these questions. If you're coming up and asking me, well, how many cards are in a deck? No, there's 52. You've now been told. Okay, so let's deal with this in a statistical kind of situation. How many different 5-card hands can be formed? Well, we don't care what the order is. You can imagine shuffling the deck and just throwing out 5 random cards. So again, that's a combination type question. We have 52 possibilities, and we're going to choose 5 of them. And that's just equal to a whopping 2,598,960. So again, 52 cards in the total deck. We're selecting 5 of them. There's over 2.5 million different ways of combining them like that. Question B now asks, how many different 5-card hands can be formed that consist of all hearts? Well, again, to select a hand that's all hearts, we only have 13 cards to choose from, the entire suit of hearts. Now we're going to select 5 from that set, which gives us a much smaller number of 1,287. So notice that when we're selecting the cards from the entire deck, we get a whole bunch of combinations, but if we're selecting it from just one suit, we get a significantly lower number, which should not surprise anybody. Now, how many different 5-card hands can be formed that consist of all face cards? Just gut instinct should tell you that it's a whole lot lower than the number of hearts, because now we have 3 face cards in 4 suits, which equals 12 total face cards, right? Oops. Which means now, out of 12 cards, we're going to select 5, and that's just equal to 792. So again, the number dropped because we have less cards to choose from. But what happens now if we start to restrict exactly what types of cards we're trying to select? How many different 5-card hands can be formed that consist of 3 hearts and 2 spades? Think back to a previous question we dealt with. You're going to have 2 situations. We're going to have the hearts. And in this case, we have 13 hearts, and we're trying to select 3. And now we have the spades, and we have 13 spades, and we're trying to select 2, which means fundamental counting principle says all we have to do is take those and multiply them together, and you will end up with the number 22,308. So a simpler type of splitting up kind of question. We dealt with this with the idea of males and females in a committee. So just a different type of question, but same process. What about E? How many different 5-card hands can be formed that consist of exactly 3 diamonds? Aha! Well, this is an interesting kind of question, because now we have this idea of diamonds, and we only have 13 to choose from, and of that we're going to select 3. However, we have everything else, because we want exactly 3 diamonds, which means we can't select any more diamonds, which means our pool of cards to choose from now isn't 52, it's 52 subtract 13, 13 being the number of diamonds, and that leaves us with 39. So for everything else, we're only allowed to choose out of 39 potential cards, and we are taking 2 from there because it's a 5-card hand. Fundamental counting principle, multiply, and we end up with the solution of 211,926. So again, similar but different. This idea up here, I'm going to put a big star beside it because you always have to think logically about what set am I allowed to select from. So let's deal with F now. F asks, how many different 5-card hands can be formed that consist of at least 3 diamonds? Well, this should ring bells from a question we dealt with earlier, we're going to have different cases. And in case 1, we're going to have 3 diamonds. And we have already dealt with that up here. So 3 diamonds has to be equal to 211,926. Now, if we have 4 diamonds, think about the question before and how we dealt with that. We have 13 potential diamonds, and we're selecting 4 from there, times we have 39 of everything else, and we're only selecting 1 of those cards, and that's just equal to 27,885. Okay, and with 5 diamonds, I think you see the pattern here. We have 13, and we're going to select 5, and we're going to multiply that by 39, but we're not going to select any of those, and that's just equal to 1,287. Think back from the idea of part B, when how many different 5-card hands can be formed consisting of all hearts. Same idea, same number, go figure. So the total then is just these 3 numbers added up, which gives you a total number of combinations of 241,098. So we just added all 3 of those there, and we get our total that's supposed to be a 9. That looks more like a 9. So split it up into 3 different cases. At least 3 hands was a key thing to look at. If it says at most 3 diamonds, then you would deal with the situations where you had no diamonds, 1 diamond, 2 diamond. So always break them up into cases. Okay? Leading on to part G, you'll notice that these playing cards questions, there's a whole bunch of different ways we can talk about this, and is completely unuseful in your future endeavors with playing cards against your friends, because honestly you're not going to do this math in your head. How many different 5-card hands contains cards with only even numbers in them? Ahaha. So step 1, let's identify the even numbers, and the even numbers in this case are what? 2, 4, 6, 8, and 10. That's it. You don't consider the queen as a 12 or anything like that. Queens are face cards, so this is it. These are your total even numbers. So there's 5 of them, but there's 4 suits, which means if we have 5 even numbers times 4 suits equals 20 possible cards to select from, which means our final answer then is we have 20 cards to select from. We're choosing 5, and that's equal to 15,504. So as I said in pretty much every other type of question, you gotta know the set that you're choosing from. If you haven't figured that out, you left out a really important part. Okay? So H asks us then, how many different 5-card hands can contain cards with only numbers 2 through 10 or are red? So there's a whole bunch of stipulations involved here. So first things first, we have to know how many cards we actually get to choose from. We know that we're selecting 5, but let's figure this out. If we have 2 through 10, okay, well 2 through 10 means there are a total of 9 cards times your 4 suits, which is equal to 36 cards to choose from. But there's more. We also said or are red. Well, we know that half the deck is red, which means there's 26 red cards. However, I'm hoping that this is raising some concern to you, because what the heck is going on here? Some of our 2 through 10s could be red. How do we deal with that? And the answer is we have to subtract the number of cards that are 2 through 10 and are red. So we know that there's 9 2 through 10s times 2 suits that are red, and that's equal to 18 cards. So you have all of these number of cards. Well, what do you do with it? Well, our original sum was we had 36 cards 2 through 10. And we have 26 cards that are red, but we want to get rid of the duplicates that we now have of the idea that there was 18 of those 2 through 10 cards that are also red. So that's what it is here. This here is the duplicates. We're getting rid of them, and that now is equal to 44 cards to choose from. That's obviously the hardest part of this whole question, because once you have that, it's a simple matter of we have 44 cards to choose from, we're selecting 5, and we're going to end up with a ridiculous 1,086,008 as our final answer. So I would say that if you were scratching your head through this entire idea here, or this idea here, rewind back, take a look again, try and understand what we were going through here. That's just coming up with all the different possible cards that we had to create our combinations, and then we subtracted our doubles. Question I is the trickiest of them all, but you know what? It's a great test question, so I would start trying to figure that out as we go along here. How many different 5-card hands are possible consisting of 2 different pairs and 1 different card? There's a whole bunch of different situations we have to deal with here, so let's just break this down and start looking at it. And let's talk about this idea of 2 different pairs first. When we have 2 different pairs, let's think about what it means to have a pair. There are 4 types of any given number in the entire deck. There's 4 2s, 4 3s, 4 4s, etc. So if we're talking about a pair, we have 4 cards and we're selecting 2 of them. That's what it means, right? But in this case, we have to key on this idea of different pairs. We can't select 2 cards from one set and then select the same 2 cards, or else we'd have a 4 of a kind. So we'll call this pair 1. Pair 2 now is going to be the exact same thing, except with a different number. So this is the idea of maybe you have a pair of 2s and a pair of 3s, a pair of kings and a pair of aces, something like that. You have 2 pairs, okay? If we then take a look at, well, this 1 different card then, we've dealt with the 2 pairs, but what about the 1 different card? So we'll just call it 1 diff here. Well, if we can't select anything from pair 1 or pair 2, we can't select from those sets, or else we'd have a 3 of a kind. It means we have to subtract these 2 4s from our total set of 52 cards in a deck, which means that we started with 52 and we're subtracting 8 cards from that, giving us 44 cards to choose from. So our 1 different card can only come from 44, and we're just selecting 1 of those. Okay, so you might think we're done here, but there's a problem, is we also haven't dealt with the number of possibilities that there are for actually selecting a pair. Which number or face card are we using for our pairs? So here, if we have choose pair, well, we know that there's 13 possible values in a deck. There is ace through king. And of that, we're going to choose 2 of those to be pairs. So that's a tricky little thing here. I'm going to put a big star behind it here. Is this idea that we have to also indicate the number of possible combinations of pairs there could be. It could be a 2, and it could be pair of 2, pair of 3, pair of 2, pair of 4, etc., etc. So this one here is a big deal, and I promise you that there are going to be a bunch of people that are going to miss this particular section a lot of the time. But if we have all of these numbers together, and if you understand why, well, wouldn't you know it, fundamental counting principle says multiply those 4 values together, and you're going to end up with a value of 123,552. The last question asks us, how many different ways can a committee of 5 be chosen from 10 girls and 8 boys so that girls have a majority on the committee? All this requires here is a bit of logical thinking about what it meant for the girls to have a majority. And in this case, we know that it's a committee of 5, which means there are 3 situations that involve girls being in the majority. And that's, again, cases. It's the idea of 5 girls, 0 boys. Yes, I did G and B. There's also the idea of 4 girls and 1 boy. And finally, 3 girls and 2 boys. After that, it would be 3 boys and 2 girls, not allowed. So that's it. That's all there is to it. And from there, we simply need to do the selecting. So we have 10 girls to choose from, and we are going to choose 5 of them. And that's going to be multiplied the 8 boys to choose from, but we ain't taking any of those. And we end up with 252 of those. 4 girls and 1 boy. Well, same idea. 10 choose 4 times 8 choose 1, and you'll end up with 1,680. And finally, we have 10 choose 3 times 8 choose 2, and that's equal to 3,360. Again, should not be surprising that the number increased as the number from each set increased as well. If all girls, no boys, it would obviously be a lot less than if some girls and some boys. So the total, add all these bad boys up, and we get the total is equal to, as you can probably see at the bottom of the page, 5,292. Oh, not 99. 92. Okay, so, my friends, that is the beginnings of combinations.